Ladies and gentlemen, when we look at our planet, we usually treat it as something ordinary, a blue ball spinning around a fairly average star in a fairly ordinary galaxy, in a universe so large that it makes our imagination feel small. And many people say, well, Earth is nothing special. But physics has a funny way of challenging things that sound simple. You see, in science we try to remove mystery, not by ignoring it, but by asking better questions. And when we ask the right questions about Earth, about its motion, its chemistry, its delicate balance of forces, we begin to notice something strange, something that doesn't quite behave like ordinary. Now imagine you are a physicist looking at planets the way an engineer looks at machines. You examine the orbit around the sun, the strength of gravity, the magnetic field shielding the surface, the atmosphere holding just asteroid gases, the liquid water moving in cycles across the surface, and the incredibly narrow conditions that allow complex chemistry to survive. None of these things by themselves look miraculous. Physics explains them all quite nicely. But when you start putting them together, one on top of another, you begin to notice that the combination becomes extraordinarily delicate. Physics teaches us something important. Systems that require many precise conditions are statistically rare, not impossible individually, but increasingly unlikely when stuck together. It's like rolling dice. Getting 16 sixes is easy. Getting 10 sixes in a row makes you start wondering what's going on. Earth behaves like that stack of sixes. Our planet sits in a narrow region around the sun, where temperatures allow liquid water. Move it a little closer and oceans begin to boil away over time. Move it a little farther and the planet freezes into a permanent ice world. Gravity is strong enough to hold an atmosphere, but not so strong that it traps thick, crushing gases like those on Venus. The magnetic field protects life from solar radiation. Plate tectonics recycle carbon through the crust, stabilizing the climate over millions of years. Each of these processes follows the laws of physics. Nothing supernatural, nothing mysterious, just equations, forces, and chemistry doing what they always do. But what becomes fascinating, what becomes physically interesting, is that the combination of all these conditions working together creates something that physics rarely produces, a long-term stability for complex life. And here's the trick that physicists like to play with ideas. We don't just ask what exists, we ask how often it should exist. If the universe naturally produces billions of planets, then we expect a wide variety of outcomes. Some will be too hot, some too cold, some blasted by radiation, some buried under thick atmospheres. Many will be chaotic systems where conditions change too violently for life to organize itself into anything complicated. So when we look at Earth, we're not just looking at a planet. We're looking at a very particular physical arrangement. Gravity, orbit, chemistry, magnetism, and geological motion, all cooperating over billions of years. And that raises an interesting scientific question. Not is Earth special? That's a philosophical question. But rather, how often should physics accidentally build a world like this? Because when physicists run the numbers, when we consider probability, stability, and the chaotic nature of planetary formation, we begin to realize something surprising. It may actually be physically difficult for a planet to remain this balanced for this long. In other words, Earth might not be extraordinary because the universe intended it to be special. It might be extraordinary simply because the laws of physics make such stable worlds incredibly rare outcomes of cosmic processes, and that leads us to a fascinating possibility. Not that Earth breaks the laws of physics, but that when we truly understand those laws, we might discover something remarkable, that an ordinary planet, according to physics, shouldn't look quite like Earth at all when physicists examine Earth. We don't begin with life, oceans, or forests. We begin with forces, because in physics, everything that happens on the planet is ultimately the result of a few simple interactions: gravity, electromagnetism, motion, and energy transfer. If those forces are arranged in just the right way, a stable world appears. If they are arranged slightly differently, the entire system behaves in a completely different manner. Take gravity, for example. Earth's gravity is not simply strong or weak. It sits in a very particular range. If the gravitational pull of the planet was significantly stronger, the atmosphere would become much thicker. Gases would be compressed into dense layers, trapping enormous amounts of heat. Temperatures would rise, weather systems would behave violently, and the surface environment would resemble something closer to Venus than the mild conditions we observe here. But if Earth's gravity were weaker, the situation becomes equally problematic. Light gases like hydrogen and helium would escape easily. But even heavier molecules that make up our atmosphere could slowly drift away into space over millions of years. Without sufficient atmospheric pressure, liquid water becomes unstable. Oceans evaporate or freeze more easily, and the delicate chemistry required for complex reactions begins to collapse. Now consider the role of Earth's rotation. Our planet spins once every 24 hours, which seems like an arbitrary fact until you realize how deeply it influences the distribution of energy. Rotation spreads sunlight across the surface, preventing one side of the planet from overheating while the other freezes permanently. Faster rotation would produce extreme winds and chaotic weather patterns. Much slower rotation could allow enormous temperature differences between day and night, stressing any stable climate system. Another force quietly shaping our planet is the magnetic field. Deep within Earth's core, moving molten iron generates a magnetic shield that extends far into space. This field interacts with charged particles coming from the sun, deflecting much of the solar wind that would otherwise strip away the atmosphere. Without that magnetic protection, high-energy particles would gradually erode atmospheric gases, a process scientists believe has happened on Mars over billions of years. The sun itself introduces another balance of forces. Earth is not simply held by gravity. It is moving sideways fast enough to remain in orbit. This balance between gravitational attraction and forward motion creates a stable path around the sun. Too slow, and the planet spirals inward. Too fast, and it escapes outward into colder regions of space. Orbital mechanics may look simple when drawn on paper, but in reality, planetary systems often experience chaotic gravitational interactions that can destabilize orbits over long timescales. Even the moon participates in this network of forces. Its gravitational pull creates ocean tides, but it also stabilizes the tilt of Earth's rotational axis. Without that stabilizing effect, the angle of Earth's axis could wobble dramatically over millions of years, causing extreme climate shifts. Ice ages could become far more severe or unpredictable, and long-term environmental stability would be much harder to maintain. When physicists put all these factors together, gravity, rotation, magnetism, orbital motion, and tidal interactions, they begin to see Earth not as a simple object, but as a finely balanced physical system. None of these forces are extraordinary on their own. Every planet in the universe experiences gravity. Many planets rotate. Some even possess magnetic fields. But the specific combination of strengths, motions, and interactions occurring here forms a system that remains stable over billions of years. In physics, we often study unstable systems because they reveal how easily order can collapse into chaos. A small change in force, a slight shift in motion, or a gradual loss of energy can transform a stable system into something entirely different. Planetary climates can run away into extreme states. Atmospheres can vanish. Surfaces can become sterile and lifeless. Earth's stability therefore becomes an interesting puzzle for a physicist, because it means that multiple forces, which could easily drift toward instability, instead remain within a narrow working range for enormous stretches of time. The laws of physics allow such balance, but they do not guarantee it will happen often. When physicists talk about planets, one of the first questions we ask is about energy. Every world receives energy from its star, and the amount of that energy determines whether the surface becomes frozen rock, boiling desert, or something in between. The interesting part is that the difference between these outcomes is not very large on a cosmic scale. A relatively small change in distance from a star can completely transform a planet's environment. Earth orbits the sun at an average distance of about 150 million kilometers. That sounds enormous, but in astronomical terms, it places our planet inside a very narrow region where temperatures allow liquid water to exist on the surface. Physicists sometimes call this region the habitable zone. It is the range of distances where incoming solar energy and outgoing planetary heat can balance in such a way that water remains stable as a liquid. Water is not just another chemical, From a physical standpoint, it has unusual properties that make it especially important for complex chemistry. It dissolves a wide variety of substances, it stores and transports heat efficiently, and it remains liquid over a relatively wide range of temperatures compared with many other molecules. These properties allow chemical reactions to occur continuously over long periods of time, creating environments where complexity can slowly build. If Earth were slightly closer to the Sun, the situation would change dramatically. Higher temperatures would increase the rate at which water evaporates into the atmosphere. Water vapor is itself a powerful greenhouse gas, meaning it traps heat and raises temperatures even further. This feedback loop can grow stronger over time, leading to what physicists call a runaway greenhouse effect. In such a scenario, oceans gradually disappear as water vapor fills the atmosphere and surface temperatures climb to extreme levels. Venus provides a striking example of this process. Although it formed relatively close to Earth in the early solar system, the slightly greater solar energy it receives triggered conditions where water could not remain stable for long periods, without large oceans to radiate there. Marotter and absorb carbon dioxide. The planet's atmosphere thickened and trapped enormous amounts of heat. Today, Venus has surface temperatures hot enough to melt lead. Now imagine the opposite situation. If Earth were positioned farther away from the Sun, the amount of incoming solar energy would decrease. Lower temperatures would cause water vapor to condense more readily, reducing greenhouse warming. As cooling continues, more water freezes into ice. Ice reflects sunlight much more efficiently than liquid water or land surfaces, meaning it sends a larger fraction of incoming energy back into space. This reflection causes further cooling, allowing ice sheets to expand even more. This process is another feedback loop, but in the opposite direction. Instead of overheating, a planet gradually freezes. Large portions of the surface can become covered in ice, reflecting so much sunlight that warming becomes increasingly difficult. Some scientists believe that Earth itself may have experienced periods in its distant past where ice spread across most of the planet, forming what is sometimes described as a snowball Earth. The fascinating point for physicists is that the habitable zone around the star is not a huge region. It represents a narrow band where incoming and outgoing energy can remain balanced over long periods. Too much energy and runaway heating begins. Too little and freezing feedback loops dominate. The range between these two extremes can be surprisingly small compared with the total size of a planetary system. Stars themselves also change over time. As stars age, they gradually become brighter. This means the habitable zone slowly moves outward as billions of years pass. A planet that begins in a comfortable position might eventually receive more energy than it can handle. Maintaining stable conditions, therefore, requires a planet not only to start within the habitable zone, but also to possess mechanisms that regulate temperature as stellar energy slowly increases. Earth appears to have such regulatory systems. Geological processes cycle carbon dioxide between the atmosphere, oceans, and the rocks, adjusting greenhouse warming over long time scales. These processes help stabilize temperature even as the sun becomes slightly brighter over hundreds of millions of years. From a physicist's perspective, the remarkable feature is that Earth remains within this narrow energy balance for such an enormous span of time, allowing complex processes to unfold across geological ages. When scientists study planets across the universe, they quickly realize that no single factor determines whether a world becomes complex or lifeless. A planet might have the right temperature but lack an atmosphere. Another might have a thick atmosphere but experience violent radiation from its star. Some worlds might contain water yet remain geologically inactive, preventing the long-term chemical cycles needed to maintain stability. What begins to appear is not a single requirement for complexity, but a law, odd list of conditions that must work together at the same time. From a physicist's point of view, this is where the idea of probability enters the discussion. Each condition taken alone is not extraordinary. Planets commonly form around stars. Many possess atmospheres, some contain water ice. Others have magnetic fields or geological activity. But the important question is how often all these properties appear together in a single place and remain stable long enough for complex systems to develop. Consider the presence of liquid water on Earth. Water is abundant in the universe, especially in the form of ice. Comets, icy moons, and distant planets often contain enormous quantities of frozen water. Yet liquid water on the surface of a planet requires a delicate combination of pressure, temperature, and atmospheric composition. Without sufficient atmospheric pressure, water boils away into vapor. Without moderate temperatures, it freezes into solid ice. A stable ocean requires both factors to remain within a narrow range over very long periods of time. Another important factor is atmospheric chemistry. Earth's atmosphere contains nitrogen, oxygen, carbon dioxide, and trace gases in proportions that allow sunlight to warm the surface without trapping excessive heat. The composition of an atmosphere is influenced by volcanic activity, chemical reactions with rocks, and interactions with living organisms. If carbon dioxide becomes too concentrated, greenhouse warming intensifies. If it becomes too scarce, global temperatures can fall dramatically. Maintaining balance requires ongoing geological and chemical processes. Plate tectonics plays a surprising role in this balance. The movement of Earth's crust allows carbon to cycle between the atmosphere and the interior of the planet. Carbon dioxide dissolves in rainwater, reacts with rocks, and eventually becomes locked into M. In noodles, through tectonic activity, some of this carbon returns to the atmosphere through volcanic eruptions. Over millions of years, this cycle acts like a planetary thermostat, preventing runaway heating or deep freezing from dominating permanently. Magnetic shielding also contributes to long-term stability. High-energy particles from a star can gradually strip away atmospheric gases if they are not deflected by a magnetic field. Mars provides a useful comparison. Evidence suggests that early Mars once had a thicker atmosphere and liquid water on its surface. But without a strong global magnetic field, the solar wind slowly eroded the atmosphere, leaving the planet colder and drier over time. Even impacts from asteroids and comets influence planetary development. Large impacts can dramatically alter a planet's environment, sometimes causing mass extinctions or major climate changes. Yet such events may also deliver water and organic molecules during the early stages of planetary formation. The timing and frequency of these impacts affect whether a planet remains stable or experiences repeated catastrophic disruptions. When physicists think about systems with many interacting requirements, they often use the language of probability and statistical outcomes. If a single condition has a reasonable chance of occurring, that does not mean the combined probability of many conditions appearing together will remain high. Each additional requirement narrows the range of possible outcomes. Planetary formation itself is a chaotic process involving collisions, gravitational interactions, and shifting orbits. Young solar systems often experience periods where planets migrate inward or outward, destabilizing smaller bodies and scattering debris across vast distances. In such turbulent environments, maintaining a stable orbit, atmosphere, magnetic field, active geology, and moderate climate simultaneously for billions of years may represent a relatively uncommon result of cosmic evolution. From this perspective, Earth can be viewed as a rare intersection of many independent processes. Gravity, chemistry, geology, orbital dynamics, and stellar energy all contribute pieces of a much larger puzzle. Each piece follows ordinary physical laws, yet their combined arrangement produces a world where complexity can grow over immense spans of time. So when we step back and look at Earth through the eyes of physics, something remarkable appears. Our planet is not simply a random rock drifting through space. It is a system where gravity, energy, chemistry, and motion cooperate in a very delicate balance. Each force follows ordinary physical laws, yet the combination creates conditions that remain stable for billions of years. And that stability is what allows complexity to grow, oceans to circulate, climates to regulate, and life to explore every corner of the surface. Physics does not say Earth is impossible. What it suggests is that such balanced systems may be far less common than we casually imagine. And that realization changes how we see our small blue world in the vast universe.